Relation between applied force and frictional force. Relation between applied force and frictional force. If a body is static, if a block is situated on another block, if we try to move the upper block by applying force, initially if we apply small force and slowly if we increase the applied force, after applying a certain force, the upper body begins to move. The relation between applied force and frictional force is studied by drawing a graph. In the graph, capital F is applied force, small f is frictional force. So frictional force is taken on y-axis and applied force is taken on x-axis. Capital F represents applied force, small f represents frictional force. Now, the relation is shown by an inclined line starting from origin O, OAB, and thereafter there is a curved path AB, and at B it is horizontal. This curve indicates that the static frictional force increases with applied force. When the body is at rest, if we apply a small force and increase this applied force, the frictional force will also increase because the body will be at rest. When the body is at rest or in equilibrium, the applied force and frictional force are equal. Hence, applied force and frictional force are equal, so we will get a straight line. As the applied force increases, frictional force will also increase. Both will have the same magnitude until it reaches a maximum value, that is represented by Fs. At A, the applied force is maximum, and this is static frictional force. This maximum value is known as static frictional force. If we slightly increase the force beyond this value, then the body comes to the state of motion. It begins to move. Once it begins to move, suddenly the frictional force is reduced. So that is indicated by Fk. This force remains constant as long as the body moves. As long as the body moves, is in motion, is in kinetic state, this frictional force is constant. So it is known as kinetic frictional force. It is known as kinetic frictional force and is indicated by Fk. Like this, we have to understand the nature of the static and kinetic frictional forces. Relation between capital F and small f, applied force and frictional force. In the curve on OA, any point on OA represents static frictional force. Static frictional force. So static frictional force is not constant. It depends on applied force. It depends on applied force. The frictional force corresponding to A is known as maximum static frictional force. The frictional force corresponding to A, it is Fs maximum. It is called maximum static frictional force. This is a constant. The frictional force corresponding to B is kinetic frictional force Fk. The frictional force corresponding to B is Fk, kinetic frictional force. So in the figure, at any point in between O and A, any point in between O and A represents static friction. So static friction is not a constant. It is equal to applied force until it reaches a maximum value. The maximum value corresponds to the point A, that is Fs maximum. So B represents the kinetic frictional force. The frictional force corresponding to B, it represents kinetic frictional force Fk. Determination of frictional force. Determination of frictional force. In the figure, take the rectangle as a wooden block placed over a horizontal table. Suppose a wooden block is placed on a horizontal table, and at the right corner you notice a circle that represents a pulley. A string tied to the block, say, passes over the pulley. Let us suppose the pulley is very smooth. The second end of this string carries a scale pan in which we place masses. So the weight of the mass, if m is the mass placed, mg is the weight. The weight acts in the downward direction and pulls the scale pan, and thereby the string pulls the block. When the block is pulled, a frictional force acts between the block and the table, that is shown as small f frictional force. So initially place small weight and slowly increase this mass or weight. So as long as the block is at rest, then mg is equal to f. So as the weight is increased, the frictional force will also increase. This is static friction. If you go on increasing this weight, after reaching a certain value, by placing a small weight in the scale pan, the block moves. So the weight just before that increase, represents maximum static frictional force. This is how we determine maximum static frictional force. Then slightly reduce the weight placed in the scale pan and give a small push to the block. Give a small push by reducing the weight. If the block moves with uniform velocity, by the push, then the weight placed in the scale pan will be kinetic frictional force. The weight placed in the pan is kinetic frictional force. Like this, we determine static frictional force and kinetic frictional force using a simple experiment. Measurement of friction. The factors on which the frictional force depends. It depends on the nature of the surfaces. Frictional force depends on the nature of the surfaces in contact. By nature we mean different substances, maybe glass, wood, marble or steel, etc. It depends on the material that is used. It also depends on the roughness of the surfaces in contact. Frictional force depends on the roughness of the surfaces in contact. It is independent of the area of contact. Frictional force is independent of the area of contact. It is tangential to the surfaces in contact. Frictional force acts tangential to the surfaces in contact. It is directed always opposite to the direction of motion. Frictional force is always, it opposes motion. Moreover, frictional force is directly proportional to the normal reaction. So to measure frictional force, we have to measure normal reaction, because frictional force is directly proportional to normal reaction. This is written as small f is proportional to capital N. Small f represents frictional force and capital N represents normal reaction. Since frictional force depends on normal reaction, first let us study normal reaction. Suppose in the left figure, a rectangle is over a long line. That rectangle represents a block placed over a horizontal surface. The weight of the block, mg, acts downwards. Because of this weight, the lower surface applies a force in the upward direction on the upper block. That is capital N. This is normal reaction. Normal reaction is nothing but reaction to the weight. If mg is the weight which is applied on the lower surface, then the lower surface applies an equal force in the upward direction on the upper surface. That is normal reaction. So normal reaction N is equal to mg, weight of the block, in magnitude. Weight acts downwards, normal reaction acts upwards. Suppose the same block is placed on an inclined surface. The angle of inclination is say theta. The angle of inclination is theta and the block is placed on an inclined surface. Then mg acts vertically downwards. The vertical arrow represents the weight mg. The component of weight perpendicular to the inclined surface is mg cos theta. The component of weight perpendicular to the inclined surface is mg cos theta. That is shown by an arrow perpendicular to the inclined surface in the downward direction. This causes normal reaction. Because of this component, the inclined surface, it applies normal reaction on the block placed. So that normal reaction will be equal to mg cos theta. Mg cos theta is perpendicular and down the inclined surface, and normal reaction is on the block placed on the inclined surface. It is upwards, not vertically but perpendicular to the inclined surface. Suppose a lorry is moving with an acceleration to the left, that is shown in the left side figure. If a vehicle is moving with a acceleration e to the left, then if a block is placed against the front glass of this vehicle, which is represented by vertical line, the vertical line represents the glass, and this glass, the rectangle, represents a block placed against this glass, then this block experiences a force ma to the right. When the vehicle is moving to the left, this block experiences a force ma to the right. Because of the force ma, the glass applies a force on the block, that is normal reaction. It is to the left. It is to the left. So the normal reaction N will be equal to ma, but ma will be to the right and normal reaction will be to the left, provided the vehicle is moving to the left with an acceleration a. Consider a body moving in a sphere, a small spherical body rolling along the inner surface of a sphere. If its mass is small m, when it is at the bottommost point, if its velocity is v, the mg acts in the downward direction, its weight mg acts in the downward direction, and mv square by r centrifugal force also acts in the downward direction. These two together produce normal reaction. So the normal reaction will be in the upward direction and it will be equal to mg plus mv square by r. mg plus mv square by r. Like this we have to compute normal reaction. Normal reaction in the case of a pulling force. Pulling force. Suppose on the block placed on the horizontal surface, if a force F is applied at an angle theta to the horizontal, represented by S, a force F is applied at an angle theta to the horizontal, then this force acts as two components. This force acts as two components, one along S, that is F cos theta. Another component is F sin theta in the vertically upward direction. F cos theta component is horizontal and F sin theta component is vertical. Of course, its weight mg acts in the downward direction. Since F sin theta is acting in the upward direction, the resultant downward force is mg minus F sin theta. The resultant downward force is mg minus F sin theta. This resultant force will create normal reaction. A normal reaction will be applied because of this resultant force. So N represents normal reaction. It will be equal to mg minus F sin theta. The component of F in the vertical upward direction is F sin theta. So the resultant weight in the downward direction is mg minus F sin theta, and this creates normal reaction. Hence normal reaction N is equal to mg minus F sin theta. Normal reaction in the case of a push. Suppose instead of a pull, if a push force F is applied on the block, F is push in this case. The horizontal component is of course F cos theta, but the vertical component is F sin theta in the downward direction. The vertical component in this case is F sin theta in the downward direction. So the net downward force on the lower surface will be mg plus F sin theta. On the bottom surface, a force of mg plus F sin theta will be applied. This force is responsible for the normal reaction. So the normal reaction applied on the upper block will be N, that N will be equal to mg plus F sin theta in the case of a push. So in the case of a push, we notice that the block is heavier than in the case of a pull. When it is pulled, we notice its weight as though it is decreased, but when we push it, we notice that it is heavier. Its weight appears to be more.